All right, welcome everybody to our first online YouTube lesson. Try watching this video, copy down the notes, make note of any questions or concerns you might have. We can chat about them in our first Zoom group session. So what we're going to do is finish off Chapter 6 by revisiting collisions. We saw them already in Chapter 5, but we're going to look at them actually in the same way and then a slightly different way here in Chapter 6. So collisions round 2. So what we're going to do is we are going to classify collisions as two general types. This is not really the hit and bounce apart or the hit and stick types of collisions we saw in Chapter 5. We're going to think about the collisions as two general types in terms of their energy. And their names are elastic and inelastic collisions. It has nothing to do with elastic bands, although you might think it does. Kind of strange names. Here's what we can say about elastic collisions. So momentum is conserved during a collision, just like we saw in Chapter 5. In fact, momentum is always conserved in all collisions. We'll make a little note of that at the bottom of the screen in a moment. What's interesting about an elastic collision is that you don't generate any heat. So the kinetic energy of the objects before the collision is exactly the same as the kinetic energy of the objects after the collision. So the kinetic energy is conserved. So these ones, they would collide silently, they wouldn't make any noise, they wouldn't create any heat. I think I'd pop up an example of what some real life ones are there in just a moment. As opposed to an inelastic, or compared to an inelastic collision, momentum is still conserved. That's always the same, just like we learned in Chapter 5. Those rules don't change. But in an inelastic collision, you do generate some heat. So the kinetic energy, just shorten it up there for you, the word, it's not conserved. So if you look at the kinetic energy before the collision, it will not be the same as the kinetic energy after the collision. It'll appear that you've lost some kinetic energy. And you didn't really lose it. Some of the kinetic energy was transformed into heat and sound. In terms of real life examples of these collision types, real life example of elastic collisions would be molecules like in the air or in water. If every time molecules in the air collided and lost some kinetic energy, they'd eventually slow down and eventually it would get really, really cold. And they're not making any noise. So we know that those collisions are elastic. It turns out that's about the only truly elastic collision I can give you. A really, really close one would be like if you're shooting pool or billiard balls. They do actually, you lose a little bit of kinetic energy, but it's a really, 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 really tiny amount. So quite often you'll see pool balls are almost an elastic collision. And then inelastic collisions, ones that do generate heat, is pretty much like all other collisions. You think about a car accident. Sometimes when cars smack into each other, they blow up, they explode. And that's because they've generated some heat energy during that collision, which makes them inelastic. So most collisions in real life that you see, demolition derbies, car crashes, football players bashing into each other, those are going to be inelastic collisions. And you've got these elastic collisions of air molecules happening around you right now. Here's another couple of things we can say. The collisions where we saw things stick together, those are always inelastic. So you know for sure you're going to have some heat energy generated. The kinetic energy will not be conserved. But that doesn't mean that the hit and bounce apart is automatically elastic. So the collisions where things hit and then bounce off of each other, they might be elastic or they might be inelastic. And it turns out we can't actually tell until we go and rerun the numbers and see whether the kinetic energy before the collision is the same or different than the kinetic energy after the collision. But what we can say about all collisions is that momentum is always conserved all the time. So that's what we did in Chapter 5. That rule is going to hold true throughout collisions round 2 here in Chapter 6. So let's try a couple of examples. I'll show you a hit and stick and a hit and bounce apart, and we'll look at the kinetic energy calculations as well. So let's try this. Here's the before scenario. We're actually going to run the same before scenario for both of the examples. So you only have to copy this down once. There's the before. After number 1, we're going to say that these objects stick together. So this is the hit and stick variety. We know that there's going to be some heat energy created. We know that this thing is inelastic because anytime objects stick together, that's an inelastic collision. So here's a couple of things we're going to do. We're going to find the final velocity. We do that using momentum. And then we're going to figure out how much energy was converted to heat. And to do that, we're going to use kinetic energy. So we're going to use EK. So let's stick with momentum. Hopefully this part is pretty easy. Remember, if you go formula sheet hunting, you're going to grab this equation. The sum of all your initial momentums equals the sum of all the final momentums. This is part A. And remember, momentum is just mass times velocity. So we've got this 8 kilogram mass traveling at 5 meters per second. And it's going to collide with a 6 kilogram mass traveling to the left at 2 meters per second. So remember, that's going to need to go in as a -2. The head-on collision is very different than one object catching another. And that is equal to these two things stuck together in the end, which is going to be 8 plus 6, 14 kilograms, moving away with some final velocity. So let's try this out. 8 times 5 is 40, plus a -12, equals 14 VF. What do we got there? 28 equals 14 VF. VF equals 2.0 meters per second. So there's the final velocity of this big object when it's all stuck together. Hopefully that's pretty easy. That is a sort of been there, done that kind of thing. We saw this type of calculation back in chapter 5. The next thing to do is to see... We're going to see if we have conservation of kinetic energy. Actually, we don't have conservation of kinetic energy, so we have to figure out how much heat was generated. So what we're going to do in this case is something very similar. To find heat, instead of looking at momentums, we're going to say that the kinetic energy initially, we're going to compare it to the kinetic energy at the end, the final kinetic energy. In this case, I'm going to tack heat onto that right-hand side because we know we're going to make some. We know objects that stick together during a collision make some heat energy. So it's going to appear that we've lost some kinetic energy. Now, if you're smart about this, remember that kinetic energy is 1/2 mv squared. Now, the cool thing is, if you look back at the equation that we used right here, you've already got m's and v's all set up for yourself. So really all we're going to do is, instead of looking at momentums before and after, we're going to tack on a 1/2, square the velocity, and we're going to turn that into kinetic energies before and after. So looking back at that line here with the arrow, the kinetic energy of the first object is 1/2 times 8 times 5 squared, plus the kinetic energy of the second object before the collision, 1/2 times 6 times 2 squared. Notice I didn't put in a -2. That's because on my calculator, if I don't put the -2 in brackets when I square it, it's going to give me a negative answer in the end. And it's really easy to forget to put negative numbers in brackets. And since it's going to become positive anyways, I would maybe suggest that when you go to do kinetic energy calculations, just leave all the velocities as a positive because they're going to be positive anyway. So that's equal to, now I've got this 14 times VF, so to turn that into a kinetic energy, it's 1/2 times 14 times 2 squared. That was the final velocity we solved for. And then we're going to have some heat. So if we throw this into the calculator, let's see what we get. 0.5 times 8 times 5 squared plus 0.5 times 6 times 2 squared is equal to 112 is equal to 0.5 times 14 times 2 squared. Yeah, you can see we're down to only 28 joules of kinetic energy on that right-hand side. And where did the rest go? Well, that turned into heat. So 112 minus 28. Looks like we've got 84 joules of heat energy created. 84 J for joules. So that's the new chapter 6 portion. That's what it looks like on a hit and stick type question. Hopefully that little pause worked. Now let's try a hit and bounce apart. So this is the same before scenario, but the after is a little bit different. We're going to say that the 6 kilogram mass rebounds to the right at 4 meters per second. And we're going to do the same thing. We're going to find the final velocity of the 8 kilogram mass. We're going to find the amount of energy converted to heat. This one, since it's a hit and bounce apart, there may or may not be energy converted to heat. We're actually not sure. We'll have to run the numbers and see. So let's start with a conservation of momentum for part A. So sigma pi equals sigma pf. Cool thing is the before the collision is exactly the same as it was. So it's 8 kilograms moving at 5 meters per second and 6 kilograms moving to the left, negative 2 meters per second, equals, now we've got the 6 kilogram mass rebounding to the right at 4 meters per second, and we want to know what that 8 kilogram mass is doing. And I think that left-hand side was 28 equals, what's that, 24 plus 8 VF. Subtract 24 from both sides, we're going to end up with 4 equals 8 VF. Divide both sides by 8. The final velocity is 0.50. Get our 2 sig figs. Meters per second. So there's the been there, done that conservation of momentum calculation to get a final velocity. And now let's go ahead and see if we can't calculate how much heat energy, if any, is created. So we're going to transition into kinetic energies. So let's see if we have EKI equals EKF. And then there may or may not be heat here. If your EKI and your EKF are the same, then your heat would be 0 joules. It would be an elastic collision. But if your EKI is bigger than your EKF, then whatever kinetic energy is lost, simply convert it into heat. Remember, kinetic energy is 1/2 mv squared, not just m and v. So we're going to look back at this line right here and just start tacking on some 1/2s and some squares on the v's. A little bit longer this time. 1/2 times 8 times 5 squared. Plus, I'm going to cheat a little bit here again, 1/2 times 6. I'm going to call this just 2 squared, so I don't have to worry about the brackets on the negative in my calculator. Equals 1/2 times 6 times 4 squared, plus 1/2 times 8 times 0.5 squared. And there may or may not be some heat. Squeeze that in there. I think that left-hand side, what did it come out to before? 112. Hopefully I'm right, because I can't edit this video. Let's see what the right-hand side works out to be. 1/2 times 6 times 4 squared, plus 1/2 times 8 times 0.5 squared. 49. So we still have some heat created. You can see that those kinetic energies before and after are not the same. So that means however many joules disappeared from that left-hand side, that simply has gone into heat. So 112 minus 49, 63. So this was an inelastic collision. We lost some kinetic energy. What did I say? 63 joules worth. There you go. I will stop this first lesson right there. What you guys can try for homework is a worksheet that's got some collisions. You're actually just going to do the front side of the worksheet. Let me actually pause you and I'll bring it up for you to see. Okay, so here's the worksheet you're going to want to try. It's posted online as Chapter 6, Worksheet 1, Collisions. It's exactly what we just did, actually, with some slightly different numbers. So I would like you to try out just numbers 1 and 2, just the first page. Don't try this page yet. That goes with the next lesson. But you can try this one out. Just a couple of clarifications here. The first collision is the hit and bounce apart. The second collision, it says the car contains the rhinoceros. That's the hit and stick collision. So the second one here is the hit and stick. The other thing you're going to want to make sure that you catch is the directions. So you'll notice in question number 1, everything's moving to the east. That's all positive. But here in question 2, north is going to be positive, but south is going to be negative. So you have to make sure you catch that when you go to do the momentum calculation. So give that a try. You will also find the answer key to that worksheet posted online. If you have any issues, come and join me for the Zoom chat session. Check your emails to see when that will happen. Take care, everybody.